Okay, so we ended with talking about geological time and how fossils have helped us trace how living things have evolved over time. So now we're going to kind of switch gears and we're going to tie in how living things have changed over time to how the Earth's surface has changed over time and how that has affected the living things on Earth. So we are going to talk about plate tectonics, ways that the surface of our Earth have changed based on things that have been happening underneath the Earth's crust. So today we are going to, our central question is, what clues suggest that continents move? Okay, and this goes with learning target 22. You should be able to state evidence and model how Pangea formed and separated. So we've mentioned Pangea before when we talked about geological time scale, and now we're going to get into how it formed, what evidence there is that it was there. Okay, so Pangea is when all the continents were joined together in one huge landmass. It happened about 225 million years ago. So again, this is a picture of what Pangea looked like. All the continents were put together. Okay, this was around the Paleozoic era. Remember, that's when the Pangea was, all the continents were all together, and then the rest of it was ocean. Okay, so who came up with this idea that land masses used to be joined and have separated? Alfred Wegener was a scientist who came up with a theory of continental drift and seafloor spreading. He said that continents were joined together in the past and that continents moved slowly. However, not a lot of people believed him. Okay, so he started to try to prove this theory that continents used to be together in the past and formed Pangea, and then they moved. But people didn't understand, well, why would our continents move? So he did not know why they moved, but he was able to show evidence that they did move. So the evidence that he found that continents move came from fossils, climate, and rocks. For example, he found fossils of same type of dinosaurs on different continents. So for example, this dinosaur was found on Africa and South America. Well, present day Africa and South America are separated by the Atlantic Ocean. Well, these dinosaurs can't swim. So he said, obviously, the Atlantic Ocean wasn't there at the time these dinosaurs were around, because if they couldn't swim, how did they get from Africa to South America? So he said that Africa and South America were once joined together in a super landmass, so that's why you find the same fossils. Same thing over here with these other types of fossils. They're found on Africa, India, and Antarctica. Well, how in the world, with the present day continents being where they're at right now, how could these be found in 3 different areas separated by oceans and they can't swim? So that's the data from the fossils that supports that continents move. We also looked at plant life. He found similar plant life. Now, here's what's really odd when you look at the climate. This is a tropical plant. He found it in Antarctica, which we know tropical plants can't survive there right now due to its cold latitude. So Alfred Wegener said, look, if we find fossils of plants in Antarctica, tropical plants, then obviously that one time Antarctica wasn't at such a low latitude. It had to be closer to the equator. So climate helped support the theory of continental drift as well. Then the last evidence that helps support, I'll get to that last thing. I went out of order a little bit. I'll get to the rock evidence in just a minute. So then he said, one of the ways that the continents could be moving is seafloor spreading. So what happens is hot magma is pushed upward through cracks in the crust. It cools and hardens and forms new crust, igneous rock. And that forms little small like mountain ranges called ridges. So here's a picture of what seafloor spreading looks like. So if the continents are moving, then that means there's going to be cracks when they separate from each other. And through those cracks, specifically in the ocean, magma is going to rise, come up through the cracks. It's going to hit the water. It's going to cool and harden and turn into igneous rock, which is in turn making oceanic crust. So that's one evidence that supports that our continents move, is that we've got magma coming up through cracks in the Earth's crust. And here's another picture. Okay, this is where those ridges I was telling you that look like small mountains underwater. Magma's coming up through cracks because these two plates are pulling apart, or these two sections are pulling apart. You look at the arrows, creates a crack, magma comes up. Okay, so another evidence that came from rocks has to do with our magnetic field. So our magnetic field surrounds the Earth, it's invisible, and it protects us against solar radiation from the sun. The reason why we have a magnetic field is because inside our Earth we have an outer core that is liquid. And because that liquid moves and it has charged ions inside it, it creates a magnetic field. Now, every once in a while, about I believe every 26,000 years, I could be wrong, I have to look that up, magnetic fields reverse, meaning the liquid in the outer core reverses directions, switches directions. So then, right now, our magnetic north points north. In a reversal, it points south. Well, rocks that contain iron, iron is magnetic, iron in the rocks will orient north and south based on where the magnetic field is pointing at the time. So if rocks are forming during reversals, irons and rocks could be pointing north in one section of rock and then be pointing south in another section. So they looked at the rocks, and what they found was that they switched directions. So this one is where a reversal happened, and the iron pointed south instead of north. Okay, reverse, reverse, reverse. So these magnetic reversals are also showing that our continents are moving because they find these in different areas. So that's the magnetic reversal, and this is showing you the magnetic, these are different layers of rocks that are oriented different directions. And right here, if you notice how they proved that the seafloor was spreading, is this blue rock was pointing one direction, this yellow rock was pointing another direction. And if these two rocks are pointing one direction, the same direction, then they've got to have formed during the same time frame when the magnetic field was pointing a certain direction. These had to be forming a certain time frame because they're pointing the same way. So it proves that our sea floor is spreading by looking at the rocks. Again, shows you another picture of the magma coming up. Then the rock that has iron in it is going to point a certain direction. These are the different colors of the reversals. So it's showing you that our seafloor is spreading. So that supported the theory that our continents move because our seafloor is moving. Okay, so in order to understand why our continents move, we have to understand about the Earth's layers, what's inside the Earth. So the outermost layer of the Earth is our crust. Okay, it's the rigid outer surface. We have two types of crust. We have a continental crust, okay, which is mostly made up of the igneous rock granite, and then we have oceanic crust, which is mostly made up of the igneous rock basalt. Okay, so two types of crust. Continental crust is obviously the crust that contains our continents. Oceanic crust is the type of crust that contains our ocean. Now, one thing you definitely want to remember is that the oceanic crust is denser. It is heavier than continental crust. Okay, then underneath the Earth's crust, okay, we have what's called the mantle. Now, there is an area that separates the mantle from the crust. We call that the morphoritic discontinuity. It's just an area that is separating the crust from the mantle. Then we get into the mantle. Okay, the mantle is made up of a solid and liquid layer beneath the crust, and it has convection currents, which I will go into in just a minute. So the mantle, the first part of the mantle is a rigid mantle. It's solid, so right underneath the crust is the rigid mantle. Then underneath the rigid part of the mantle, the next part of the mantle is the antiosphere. This is the part of the mantle that flows. Okay, so why does it flow? Well, you've got, when warm matter heats up, it has more kinetic energy. When it has more kinetic energy, it's going to rise. So this liquid has warm magma rising. When the magma rises, it starts to transfer some of that kinetic energy to the other parts of magma. When it transfers that kinetic energy, it loses some of the kinetic energy, so it gets colder. And when it has less kinetic energy, it's denser or heavier and it sinks. Okay? This forms what's called convection currents. So as warm magma rises, cools and then sinks, you're getting what's called a convection current. That's what creates the flow of magma. And if our crust is sitting on the mantle and the mantle moves, then so does our crust. And then therefore we have continents moving. Okay, so because we have a liquid layer in the mantle called the called the antiosphere. That's what I want. I don't want the blue. I'll just click on that. Okay, because we have this antiosphere, this is what's causing plate movement. Okay, so you might want to make sure you add right here, this is what's causing our crust to move because of convection currents in the mantle or in the antiosphere. Okay, so convection currents are what's going to create the flow of magma in the antiosphere, in the mantle. And since our crust sits on the mantle, that's what's going to cause our continents to move. Okay, now we classified the crust and just the rigid upper part of the mantle, not the antiosphere. We call that the lithosphere because that's the part of the earth that doesn't move. So the part of the earth, that's the part of the earth that is a solid part. So the upper solid part of the earth, the crust and the upper mantle is called the lithosphere. Okay, then underneath the mantle, you have the core. Okay, the core is underneath the mantle and it's divided into two parts, the inner and outer core. Okay, the outer core is a liquid layer that creates our magnetic field. That's one of the ways we were able to support that the seafloor spreads. Okay, the inner core, because it is under immense temperature and pressure, you have a solid, which is basically made up of iron and nickel, the elements iron and nickel, because they're one of the heaviest elements, so they sunk to the core of our earth because they're heavy. Okay, so hopefully after today you've got a better idea of some of the ways that we can support that our continents move, and now you've got a better idea of what the underneath the earth's crust, what it looks like, and kind of why our continents move.